Hey everyone, Mr. Hauk here. In today's video, we're going to be introducing limits. Now, with this being a pre-calculus course and this being technically a calculus topic, we're not going to go extremely in-depth with limits. In fact, over the next several videos as we introduce limits, you're going to get a very kind of introductory exposure to it, okay? The goal for this video specifically is going to be finding limits using a table and just generally understanding what a limit is. So what a limit is it tells us the value that a function approaches as that function's inputs get closer and closer to a certain number. So let's kind of look at our first example here. Now, first off, let's talk about notation. We see right here, let me get a laser pointer. This is limit notation. And what this is saying is this says the limit, that's what lim, limit of f of x, the function, as x approaches c. Okay, so this is saying the limit of f of x as x approaches c. And what this is it represents the y-coordinate that f of x approaches as the x values get closer and closer to the c value. Okay, so let's do this through a table. And the first thing that I want to actually do is I want to use a table to figure out, well, what happens at that specific value? What happens with this function f of x at 1 specifically, because we're concerned with what happens as x approaches 1. Well, let's look and see what happens first when x is equal to 1. So you can use a graphing calculator and make a table. You can plug in these values by yourself. I'm going to plug in a value real quick. So if I want to take 1, the input, and plug it into the function, well, we would just plug in 1 for all the x values. So if I plugged in 1 cubed minus 1 over 1 minus 1. Well, 1 cubed minus 1, that'd be 1. We get 1 minus 1 over 1 minus 1, that'd be 0 over 0, which is undefined. 0 over 0 is not, it's an undefined value. So at 1 specifically, this function is undefined. So we can't rely on what the function is at 1 specifically. Let's start looking around 1. So the input value is really close to 1, would be something like 0.99, 0.999, 0.9, or on the right side of 1, the inputs to the right of 1 would be 1.001, 1.01, 1.1, just values that are really, really close to 1, which is what we're really interested in. We want to know what's happening to the function values as we approach 1 for the x values, the inputs. So again, you can either plug these inputs, all these x values, you can plug them into the function itself to get the value, but I'm going to actually use Desmos and create a table of values. So you can see over here I've got a Desmos screen. Here's x cubed minus 1 over x minus 1. Notice that at the input of 1, if I put a little marker right there, you can see that at 1, the function is undefined, okay, because it creates a 0 in the denominator. We can't divide by 0. So if I click on this little settings wheel and I click on the table icon, I can actually turn this into a table. So let's figure out what happens, and I can adjust it myself. Let's figure out what happens when x is 0.9. Well, when x is 0.9, the function value is 2.71. Okay, let's see what happens when x is 0.99. Well, now the function value is 2.9701. Okay, and what about when x is 0.999? So we're starting to get really, really close to 1. Well, now the y value, the function value, is 2.997001. I'll just put 2.997. Okay, so that's coming towards 1 from the left. Now let's look slightly to the right of 1. Let's look and see what happens when the x value is 1.001. Really close to 1 on the right side. Well, now it's 3.003001. Let's just put 3.003. Okay, what about when x is 1.01? Oh, go back. This one, 1.01. Well, we get 3.0301. And then lastly, let's look at 1.1, we get 3.31. Okay, so let's look at the pattern here. If we look at the function values, as the x values get really, really close to 1, well, as we start getting really close to 1 from the left side of 1, we can see it goes 2.7, 2.97, 2.997, and as we get close to 1 from the left side, 3.003, 3.0301, 3.33 or 3.31. So as we close in on 1 from the left and the right, these function values are getting really, really close to 3. Now, it's not equal to 3. It's something that's very important to understand about limits. Limits aren't, what does the function equal at this value? It's what does the function approach as x approaches that value. So as x approaches 1 from both the left and the right, the function values, the f of x values or the y values, are approaching 3. And the way that we would write that is we would say the limit of f of x as x approaches 1 is equal to 3. Okay? So that's our first example. Looking at our second example, well, let's do more of that same process. This time we have a new function value, or we have a new function rather. We want to find the limit of x squared minus 3x plus 2 over x minus 2 as x approaches 2. So once again, let's go ahead and let's close this one down. Looking at this, let's go ahead and turn this into a table just to get quick access to the function values. And let's start to approach 2 from the left and the right. So first, let's look and see what happens. Well, first, let's look and see what happens at 2. Notice that when x is equal to 2, the function values are undefined. Again, that's because if you look in the denominator, if I plug in a 2 here, 2 minus 2 would give me 0, and we can't divide by 0. So 2, an input value of 2 would be undefined. Let me zoom in here and write this correctly. Undefined. Okay, so we don't know what's happening at 2. Let's look around 2. So let's start at 1.9 and start to get closer and closer to 2. So, 1.9, there we go. So if x is 1.9, f of x, or the y value, is 0.9. Well, if x is 1.99, then the y values are 0.99. If x is 1.999, then the y values are 0.999. So as we approach from the left, it looks like these numbers are getting closer and closer to 1. 0.999 is practically 1. Let's now approach from the right side. Let's go from 2.1 to 2.01 to 2.001. Start getting really close to 2 from the right side. So starting with 2.1, we get 1.1. Now let's make x 2.01. Now we get 1.01. And now let's make the x value 2.001. And we get 1.001. So we can see that as we approach 2 from the right side, these f of x values, the function values, are getting really close to 1. And now let's look at the two sides combined. So as we approach 2 from the left, these values are getting really close to 1. As we approach 2 from the right, these values are also getting really close to 1. So we would say that the limit of f of x as the x values approach 1, or sorry, as the x values approach 2, is equal to 1, because that's the function value that we're approaching. Okay? So let's look at some other examples. Our next example here, we want to look at the limit of the absolute value of x divided by x as x approaches 0. Notice this time in our table, we're not given any function value or any x values, any inputs. So we're going to go ahead and create them. First though, let's go ahead and get rid of that table. So we're dealing with the absolute value of x over x. And as we look at this table here, we know that the input value that we're interested in is 0. So I'm going to put that in the middle of my table. Let's put that right. Let's go black here. Input value of 0. Looks a little sloppy. Okay. Now, watch what happens though. If we plug 0 into the function, you put 0 in for x, you're going to get 0 on the denominator. So we can already tell that at 0, this function is undefined. So we can't rely on looking at 0 itself. So let's look to the left and right of it. Well, to the left of 0 would be negative numbers. Be negative numbers like, let me go blue here, negative 0.001, negative 0.01, negative 0.1. Notice as we move this direction, they're getting closer and closer to 0. And just to the right of 0, we'd have things like positive 0.001, positive 0.01, positive 0.1. Okay, as we move this way, we're getting closer and closer to 0. So let's use our table, or let's make a table. Let's figure out these values. Okay, so and again, we can see in the table 0, we get an undefined value. Let's start from the left side. Negative 0.1, 0.1. We get negative 1. Okay, well, what about negative 0.01? We got negative 1 again. And now let's do negative 0.001. And we get negative 1 again. As it turns out, this one's actually really easy to just go ahead and plug these inputs into the function. Very, very quick and easy. Okay, from the right side, let's start with 0.1, positive 0.1. Well, there we're going to get positive 1. No, get the pen. There we go. Okay, let's put in positive 0.01. Here we'll get positive 1, and then we'll put in 0.001, and that'll give us positive 1 as well. So here we notice something different from the first couple of examples. Notice that as we approach 0 from the left side, it looks like all the function values are negative 1. But as we approach 0 from the right side, all the function values are positive 1. So what this means is that the limit actually doesn't exist, because as we approach from the left and we approach from the right, we're getting different function values, totally different function values. We're not approaching the same number. So we would say that the limit of f of x, in this case f of x is absolute value of x over x, as x approaches 0, does not exist. D and E meaning does not exist. Okay, and we can see the justification right here. Oh, the highlighter here. The limit from the right side and the limit from the left side must converge to the same value for the limit to exist. So on the left, the limit is converging to negative 1. On the right, the limit is converging to positive 1. These two numbers are not equal to each other, so the limit as x approaches 0 does not exist. The left and the right side limit are not equal to each other. Okay, let's try another one. So here, our function, we want to find the limit as x approaches 0 of 1 over x squared. And again, we're worried about as it approaches 0. So let's put 0 in the middle of our table. That's really the important value here. Okay, but if we plug in 0, we can already see it pretty clearly. 1 over x squared, we plug in 0 for x, 1 over 0 squared, we get 1 over 0. We're not allowed to have 0 in denominator, so this is undefined at 0. Okay, so let's start looking left and right of 0, just like we did in the previous example. Let's go black here. So negative 0.1, negative 0.01, negative 0.001. To the right of 0, we'll go 0.001, 0.01, and 0.1. Okay, so slightly to the left, slightly to the right of the input 0. As we start to plug in some numbers here, and let's go ahead and turn to our handy dandy table from Desmos. Again, you could do this with a TI-84 graphing calculator as well, or you could just plug in the values. But let's see what happens. So let's go negative 0.1. We get 100. Let's go negative 0.01. We get 10,000. And then negative 0.001, we get 1 million. So if we look at the pattern here, it looks like the closer and closer we get to 0, the function values, the y values, are just blowing up larger and larger. Okay, so as we get closer to 0, this thing is growing out of control. It's growing without bound. Let's look and see what happens on the right side of 0 with 0.001 and 0.01 and 0.1. And I got a feeling it's going to do pretty much the same thing. So let's start first by looking at 0.1. Start moving in from the right side. Well, it looks like we're going to get 100. Okay, if we plug in 0.01, we get 10,000, so it's pretty much mirroring itself. And we can already guess, and you can check if you want to. But if we plugged in 0.001, we'd get 1 million. So this is going to be another example of a limit that does not exist. Because, while it might look like at first, this looks like from the left and from the right, they're approaching the same thing, but they're both on both the left and the right of 0. The function values are growing without bound. And what that means is the closer we get to 0, these function values are just getting bigger and bigger and bigger. So it's not really approaching any value. So what we would say is that, again, the limit of f of x being 1 over x squared, as x approaches 0, does not exist. Okay, let's do one more example in these notes. So in this example, f of x is equal to 1 if x is not equal to 2, and f of x is equal to 0 if x is equal to 2. And for this, we're not going to need Desmos at all, so I'm going to go ahead and swipe that over. So we are interested in what is happening, what the function is approaching as x approaches 2. So let's put 2 in the middle of our table. Okay, right here. Well, at 2 specifically, when x is equal to 2, f of x is equal to 0. And let's look to the left and right of 2. So to the left of 2, we would have, really close to 2, we'd have like 1.9, 1.99, 1.999. To the right of 2, we'd have things like 2.001, 2.01, 2.1. So these are just values immediately to the left and right of 2, okay? But this is really simple to figure out, because if x is not exactly equal to 2, then the function value is just going to be 1. Well, 1.9 is not exactly equal to 2, so the function value is just going to be 1. 1.99 is not exactly equal to 2, so the function value will be 1. Same thing here. 1.999, that's not exactly equal to 2. Function value would be 1. 2.001, not exactly 2. It'll be 1. 2.01, not exactly 2. Function value would be 1. And then lastly, 2.1, again, not exactly equal to 2. So the function value would be 1. So this one, we look at it and we might be tempted to say, okay, well, at 2 itself, the function value is 0. So the limit must be 0, right? But that's not how it works. The limit is what the function values are approaching as we get closer and closer to 2. It is not what is the value at 2, it's what the function values are approaching as we get closer to 2. So from the left side, the function values are all going to 1. From the right side, all the function values are going to 1. So the limit, as x approaches 2 of f of x is equal to 1, because that's what we're approaching. That's what the function values are approaching, okay, on the left and the right side. Another way we can look at this real quick, we can say the limit as x approaches 2 from the left. You see this little minus sign in the exponent next to 2? That means as we're approaching 2 from the left, well, the limit as x approaches 2 from the left is equal to 1. But the limit as x approaches 2 from the right side is also equal to 1. And we would write that as the limit as x approaches 2 from the right. So the limit as x approaches 2 from the left, the little minus sign means from the left. This little plus sign in the exponent means from the right. And notice that these two limits are the same. So that means that the limit as x approaches 2 overall is going to be equal to that value 1. Okay? And what's important to realize here is that whether or not f of x even exists at the input that we're interested in has no bearing on the existence of the limit itself. We are looking at what do the function values approach around this x value of 2. Okay? So this is a very, very brief introduction, limits from tables. The big takeaway here is we are not really interested in the function value at the specific input we're looking for. We're looking at what's happening around that input. Okay, that's going to determine the limit. And what we're looking for is the input or the function values to the left and right of that input to be the same. Like for example, in example 1, from the left, we can see the function values approaching 3. From the right, we can see the input values approaching 3. So the limit was 3 at the limit as x approached 1. Same deal here in the second example. From the left, function values are approaching 1. From the right, function values are approaching 1. So the limit as x approaches 2 is equal to 1, because the left and the right side limits were the same. But then we saw examples like in the third example. The limit from the left side as x approached 0 was negative 1. The limit from the right side as x approached 0 was positive 1. These function values are not approaching the same value, so the limit does not exist. Same deal here. From the left, from the right, the function values are blowing up out of control. They're growing without bound, which means that the limit does not exist. And then in our final example, from the left, function values approach 1. From the right, function values approach 1. Left and right side limits are approaching the same values, so the limit as x approaches 2 is equal to 1.